So we will conclude with an example. We're going to take a vector field f, which is equal to 2x plus 5y, and then 5x plus e to the y. And then I'm going to find the integral from 0, 0 to 1, 2 of f dot dr. And I'm not going to specify a path. I'm going to show that this integral is path independent. And so I don't have to specify a path, and I can use the fundamental theorem to evaluate this integral. Okay, so let's start by showing that capital F is conservative. So capital F is conservative. Okay, because the derivative with respect to y of 2x plus 5y is 5, and the derivative with respect to x of 5x plus e to the y is also equal to 5. Okay, so this is p, that is q, and so dp dy equals dq dx. That's how we show that a vector field is conservative. Okay, well, now that I've shown this vector field is conservative, that means that this integral must be path independent. So I can use the fundamental theorem. I can find a potential function and use that to evaluate this line integral. Okay, so we're going to find a potential function. We're going to do that by saying that p is actually the derivative of the potential function with respect to x. So p in this case is x, or 2x plus 5y. So I'm going to find the antiderivative, and that tells me that f of xy is going to be x squared, integrating the 2x with respect to x, plus 5xy, plus some function of y. We'll call that function c of y. Okay. So that is my potential function, but it's arbitrary up to some function of y. So I'm now going to take the derivative of that with respect to y. The derivative of x squared is going to be 0. The derivative of 5xy is going to be 5x. And then the derivative of c of y is c prime of y. And then I'm going to set that equal to q. Okay, I'm going to set that equal to 5x plus e to the y, because again, we should remember that p is supposed to be the derivative of our potential function with respect to x, and q is supposed to be our derivative of the potential function with respect to y. Okay. So now I can compare these. Look, there's a 5x there and a 5x there. And so that tells me those are going to cancel. And c prime of y, in fact, is equal to e to the y. Okay. So that means that c of y must be e to the y. Now, you would normally say plus a constant, but we're going to evaluate this antiderivative, we're going to evaluate this line integral using this potential function, kind of like we evaluated integrals using antiderivatives, and you don't need to use the arbitrary constant when you're evaluating using potential functions or antiderivatives, right? That arbitrary constant would subtract out. And so we don't need that. We just need to find a potential function, not the potential function. Okay, so in fact, that tells us that f of xy then is going to be x squared plus 5xy plus e to the y. So if I want to integrate from 0, 0 to 1, 2, f dot dr, I can do that by essentially evaluating my potential function at the two endpoints, f of 1, 2 minus f of 0, 0. So f of 1, 2 is going to be 1 plus 5 times 1 times 2 plus e to the 2. And then if I evaluate the other one at 0, 0, I'm going to get 0 plus 0 plus e to the 0. So in fact, this integral becomes, kind of canceling out the 1 and the e to the 0, I'm going to get 10 plus e squared. And so now I've evaluated this line integral that turned out to be path independent just by evaluating the potential function at the two endpoints. So let's summarize what we've learned here, because there's a lot of equivalent statements that we can make. Capital F is going to be a vector field, PQ, defined on a region D. And it turns out all of the statements I'm about to make are equivalent. F is conservative. So suppose that F is conservative. Well, we learned in a previous lesson that meant that dp dy equals dq dx on a region D. Okay. And we also learned in a previous lesson that F has a potential function such that the gradient of little f is equal to my vector field capital F. But in these lessons on path independence and the fundamental theorem, we've also learned that if f is a conservative vector field, that the line integral of f dot dr is path independent. We've learned that we can use the fundamental theorem of calculus for line integrals to say that if the path C connects the points A and B in D, then we can evaluate that integral of f dot dr using the potential function little f. And then also for conservative vector fields, we have that the integral around any closed path of a conservative vector field is going to be 0. So all of these statements are equivalent. So if you're able to show one of these things, for example, if you're able to show this, then all the other 5 statements are equivalent. If you were able to show that an integral of f dot dr equals 0 anywhere throughout the domain D, okay, then you must have a conservative vector field, and all of the other statements must be true. So these are some fun equivalent statements about conservative vector fields, and they show you why it's important to have this designation of conservative vector fields.